Let's do a video about enthalpy change. This is chemistry pace 1128. We're going to talk about setting up the problems on page R, problem 22 and 23. And as I'm looking at this, I'm saying, wow, I feel bad that my handwriting is so horrible. It's like I'm writing on a whiteboard, which I am. It's just on an iPad. But I'm telling you, it's a lot faster doing it this way than using a keyboard. So I'm sorry it's a little sloppy, but we'll get to the content here in just a second. The graph in your text part of the pace shows this red arrow, okay? And it shows there's numbers and letters, and there's all this terminology in here. It looks a little confusing. And even when you read the text part of the pace, there are all these variables with subscripts, and they're all brand new. And then they insert these formulas, and then they have a lot of numbers with positives and negatives, and then they have the units coming after them. I don't know, it just looks like a mass of jumbled information, kind of hard to sort out and get your brain around it. At least if I were a teenager working through it, I think I would be a little overwhelmed. So I just want to kind of draw out a couple of things and suggest something to you, all right? This information that I have over here on the right, I think would be wise for you to, at some point after I explain it, stop the video and copy it into the text part of your pace right above graph 8.1, okay? So there really are only like 3 or 4 variables, and they're all E's, okay? Because E stands for energy. So the subscript tells us what it's for. So ER is the energy that is embedded in the bonds of the reactants. EP is the energy embedded in the bonds of the products, okay? So that makes sense. EA is what's called the activation energy. Think about it. Do you know that paper burns, right? If you had a bunch of wadded up paper, or if you had some logs and you're wanting to warm up around a fire, you can't just lay the logs there and assume the fire is going to start on its own. You have to give it some energy. So you have a match, maybe you have some lighter fluid on it first, you get some paper started. And the idea is once the reaction gets going, you add some energy to it, and it gets up to a point where now the reaction can go forward on its own. And it'll just keep going and going and going and going. That is the activated complex, AC, all right? At that point, it will keep feeding itself. And so it's just like burning a fire. And let's say burning a log, in a fire. Once you add some paper and a match and you get it going, that's like adding the activation energy. Once it's started, it just keeps going and going and going until all you're left with are the products, the ashes, and there's water vapor and carbon dioxide that's given off, okay? So let's look here. The activation energy is what you're adding to it to get it started. And then the formula for figuring out the activation energy is we're going to take the activated complex, which is the highest point, okay, and subtract whatever the reactant energy level was. So the difference between those two. So that's this arrow right here. So we just, in this case, had to add a little bit of energy to it. The reaction takes place, and then the products are way down here. So the difference between the reactants and the products is called the delta H, the change in enthalpy. Notice this is negative. A negative change means that it has given off thermal energy. It's usually in the form of heat and light, maybe like fire, an explosion of some type. But energy has been given off. This is exothermic. Reactants start off here, the products end up at a lower energy state, okay? And again, notice the difference between these two is the delta H, the difference between where we started and where the reaction can begin to happen on its own is the activation energy. So we have a formula here, EAC, the peak, the highest point, minus where the reactants start, is the activation energy. And then the change in H, the delta H, is the products minus the reactants. Okay? So again, if you would just write all of this down at the top of that column above where it says graph 8.1, and then keep referring to that while you read through that page, I think it'll make more sense. All right, now let's move on to the next graph, 8.2. This is what an endothermic reaction looks like. So notice the products start low. We actually have to add a lot of energy to get it up to a point where the reaction takes place, okay, the activated complex. But at that point then, the reaction takes place and the products are formed, and the products have more energy in their bonds than what the reactants had to start with. But somehow energy had to be added to it. So the difference between the peak, again, the starting point of the reactants and the peak, is the activation energy. Then the difference between where we started and the final products, that is delta H. And notice in this case is positive. So notice for endothermic reactions, we have a very large EA value. The energy of the products is higher than the reactants. And notice that we have a positive delta H. All right, so now let's help you figure out how to set up this problem, all right? A reversible reaction system in equilibrium has the following values. So we have the ER value, we have the EP value, and we have the peak, all right, of our graph. So looking over here, I just drew this little chart just so I can visualize, because that helps me. So the reactants start down here, and reactants, it tells us, is 0. Okay, so they're starting at 0. We have to go all the way up to 100 for the activation complex to begin, and then the products end up here at 50. So think about what this means. The delta H, okay, is the products minus the reactants, so that would be like the difference between here and here. Okay? Let me quick change out the color here, and I'll use yellow. I don't know how visible that will be, but let's try it. Now we're also supposed to find the activation energy, and that is the difference between the starting point, ER, and the highest point, the peak. So that's between here all the way down to here, okay? So now we can visualize it. Sometimes I think the graph is easier to read than doing all the math, but here's the formula. They give us the numbers up here at the top, and we can plug these numbers into either this formula or to this formula and solve, okay? So I don't think that's too hard. Now they talk about a reversible reaction, and that's saying, what if we actually started here, called this the reactants, and we're going here to this being the products? Now notice, I didn't talk about this, but did you recognize whether this was an endothermic or exothermic reaction? Hopefully you said endothermic, okay? But when we reverse it and go the other way, it's an exothermic reaction. Notice when we go from here to here, the delta H ends up being the same. It's just the opposite sign, okay? Now it's a negative number because it's giving off energy to go from here to here. The other thing you need to notice is we're only going from 50 up to 100, okay? So the difference between these two is going to be the activation energy for the reverse reaction. The other thing to use this formula, either one of them, notice they don't tell us right off what the ER value is. And same thing with problem 23. They don't tell us what the ER value is. But as you read in the we're always just going to assume that ER is equal to 1. We'll start with the reactants being 0 because we're actually just looking for the change in enthalpy. So we don't need to measure a number to start with. Let's just call 0 our starting point. And then from there we can plug in the numbers and figure out the change in enthalpy. All right. I know this section may seem a little confusing at first. As you dig a little deeper after watching this video and try to do these problems, I hope that it will make more sense to you.